Good afternoon, students. Today we are going to discuss one important topic, that is electric potential due to an dipole, electric dipole, and the concept of equipotential surface. Okay, right. So these ideas are fundamental to understanding electric fields and electric fields and have incredible real world applications. Just think about Michael Faraday, who, despite having limited resources, visualized these abstract concepts. His curiosity led to the discoveries that power our modern technology. Okay, like Faraday, we can unlock real world application by exploring these concepts, these ideas. Okay, right. So let's start with a quick quiz to refresh our memory on some concepts which is you studied in previous classes. Okay, so I will share the screen now. Yes. Okay. Done. Okay. Right. So first question: what is the SI unit of electric potential? Already you know that electric field and the electric potential. So what is the SI units? Think about it. If you know the answer, you can message me via the chat box. Think, what is the SI unit of electric potential? First of all, you have to think about electric potential formula. Yeah. So in terms of dash, we can derive electric potential. What? In terms of what? Already you are familiar with that word potential. Yeah. Okay. Good. Old. Very good. KGBV Anandapuram. Good. Any other responses? Any other students? Please. Okay. Oh, good. Very good. AB. URJC. Yes. Good. Old. Very good. Good. Good evening to all. Okay. Okay. We can choose first option, old. We can check it later. Okay. Good. Then we can move into that second MCQ. The work done in moving a charge in an electric field depends on. Already you are familiar with that word, charge and the electric field, and as well as work done. Suppose if you done work by moving a charge in an electric field, that work depends on path taken, initial position, final position, both initial and final position. Which one is correct? Yes. Option D. Okay. Good. Option D. Very good. Good. Okay. Super. Very good. 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 Option D. Yes. Both initial and final position. Okay. Good. So the work done depends on Initial and the final position. Okay, good. And the final one, very crucial MCQ. Very, very important one word. The electric field is the negative gradient of dash. Charge, potential, force, current. B, C, B, C. Okay. B, C, D. Okay. So which one is correct? Exactly correct. Charge, potential, force, current. B. C. Okay. Let me check. Okay. Right. So the electric potential is the negative gradient of potential. Already you know that formula. Electric field C is equal to minus dV by dx, or we can write it d minus dV by dr. Okay. So potential. Okay. Submit. We can check that answer. Yes. What is the SI unit of electric potential? Volt. The work done in moving a charge in the electric field depends upon good both initial and final positions. And the final one, the electric field is a negative gradient of potential. Very good. Good responses. Great student. Yes. Very good. Negative potential. Yes. Good, good. Super. Clear. Okay. So, all right. Let's get into that main concepts. First of all, here electric potential due to dipole. Okay. So, what do you mean by dipole? What do you mean by dipole? Di means two. Yeah. Pole means already you know that there are two poles. One is North Pole, South Pole, like that. Yeah. So dipole means two. Yes. So here, in terms of charge, dipole is a pair of equal and opposite charges. Equal and opposite charges. So, for example, we can take plus Q minus Q. So this is a positive charge, this is a negative charge, and their magnitude will be equal. So for example, this is a 5 plus 5 coulomb. This is also minus 5 coulomb. This is 7 nano coulomb. This is also minus 7 nano coulomb. Yeah. So equal value, but opposite charges. Correct? So which is separated by the small distance like 2a. So for example, here minus q, here plus q. So here origin between this charge to this charge distance to a. That means the distance between that any one charge to origin is a, like that. Okay. So then only we can say the distance between these two charge will be equal to 2a. Yeah. So this is the electric dipole. Dipole means two, electric means charges. So two charges placed like that. This is the scene. Okay. We need to find the potential. We need to find the potential at some point. We can choose that point like that, for example, here, or for example, here, or for example, here. Okay. So look at that some distance from that system, from that center of the dipole, like that. Okay. So that point P makes an angle theta with the dipole axis. For example, here also theta, here also theta, here also some theta. Yeah. Okay. So we need to find the potential at the point P, which is located at a distance R from the center of the dipole. Yeah. Okay. So we can place a two charge in a space like that. Plus Q and minus Q. And here origin. Okay. We can choose point here P. Okay. Right. This is the distance of 2A. Okay. This is A. This is A. Okay. So this is origin. We have to draw one line from the center of the dipole to that point. In this point, we have to find the electric potential. Yeah. Okay. So R1 is the distance of plus Q to P. R2 is the distance of minus Q to P. Then finally, R here is the distance of center of the dipole to the point P. Clear? Okay. So the potential at P due to this point positive charge plus Q we can write V plus Q because the potential at point due to plus Q charge. The formula is 1 by 4 by epsilon naught Q by R1 because R1 is the distance. Like that, the potential at point P due to minus Q, which is the negative charge. Yeah. So then we can write V minus Q. Okay. Then same formula, but minus Q charge here. So R2. So this is the potentials. Okay. But in this point, that means at a point P, the total potential means sum of these two potential because in this point, this charge provide one potential and after that if we place the second charge here it's also influence that field influence that potential so potential may be vary or degrees okay so vary increase or degrees okay right so total potential means we have to add these two potentials okay right so then final potential V is equal to okay sorry so final potential V is equal to V plus Q and V minus Q. Here you can see that Q by 4 pi epsilon naught is common term. But sign, that is negative sign, only the difference in that second equations. So we can write like that. Q by 4 by epsilon naught 1 by R1 minus 1 by R2. Clear? Okay. So now by geometry, we can write R1 square equal to R square plus A square minus 2A R cos theta as well as R for R2 square R square A square 2AR cos theta. In this case, R double greater than A. So we take R much greater than A. So in terms in terms of R, for example, R1 square, R square plus A square, because you know that. So this is R, this is A, this is R1. So R1 square is equal to, this is theta. So R1 square is equal to R square minus plus A square minus 2AR cos theta. For R2 square, R square plus A square plus 2AR cos theta. So we can take R much greater than A. So in these equations, we can take the R as common. So R1 square, R square. So 1 plus A square by R square. Here R square common. So that means like that. Yeah. R double greater than A means R much greater than A. So we can neglect A here because this is a very small value. This is a very huge value. So if we divide the small value with very much high value, that value nearly close to 0. Yeah, very much close to 0. So we can neglect like that. So 1 minus 2A cos theta by R. Same process R2 R square plus 1 plus 2A cos theta by R for the R2 square. So using the binomial theorem, we can write 1 by R1, 1 by R2, and finally we can write D. Okay. For example, V. So here V means total potential. Is it correct? So already we know that. So this is the equations. Already we knew that. Yeah. 1 by 4 by epsilon naught Q by R1 minus Q by R2. We can take Q as common. So 1 by R1, 1 by R2. We have 1 by R1 means 1 by R, 1 by 1 minus 2A cos theta by R whole power minus 1 by 2 for 1 by R1. So we can simplify. So approximately 1 by R. This minus 1 by 2 goes here. So 2 cancel and minus into minus plus. Already you know that. So 1 plus A by R cos theta. So this is all for R1. That means 1 by R1. Okay. For 1 by R2, for 1 by R2 is approximately 1 by R 1 plus 2A cos theta by R minus 1 by 2. So here plus, here minus for the R2. So the minus 1 by 2 goes here and 2 cancel and minus into plus minus. So approximately 1 by R equal to 1 minus A by R cos theta. Now we can substitute the 1 by R1, 1 by R2 here. So we will get B is equal to Q by 4 by epsilon naught, and you can cancel that any common terms. So finally we can get 2A cos theta by R square. Yes, 2A cos theta by R square. Already we know that electric dipole moment P is equal to 2QA. Here you can see the 2QA. So we can place P cos theta by 4 by epsilon naught R square. This is a total potential. This is a total potential at the point P. Okay. So here you can note one important point, very, very important point that is, so this is the total potential for the electric dipole. So there are two charges, equal and opposite charges. Here you can see that 1 by R square. But for the single charge, for the single point charge, 1 by R only. Yeah. So the potential from the dipole inversely proportional to the 1 by R square term. But for the single point charge, it is inversely proportional to the 1 by R. That is directly proportional to 1 by R or inversely proportional to the R. Okay. So it is directly proportional to the 1 by R, but for the potential from the dipole is directly proportional to the 1 by R square. Very, very important point. Note it down. Okay. Right. Now, so these are all for the electric potential due to dipole. Note the important equations, formula. Okay. Now, let's talk about special case. That is equipotential surface. Equipotential surface. Okay. So before that, we can see that one simulation, one animation for that electric dipole. I will share the screen now. Okay, please wait. Sorry. Okay. Now I think okay. Yes. So here you can see that charge. That is plus 1 nanocoulomb. NC means nanocoulomb. Correct? We can place like that. Okay. And we can see the value of the potential and the electric field. For example, for this point, you can see that electric field 37.8 volt per meter. Okay, this is the value of electric field. Now, here, okay, so 31.2 volt per meter, and I will go to from this position to this position. You can see that the value decreases. So away from the charge, away from the positive charge, the electric field decreases. Yeah. So very close to the charge, the potential, that is electric field is high. Like the same way, we can choose another one charge that is minus Q here. Here you can see that electric field lines that is emanate from that positive charge and terminate at the negative charge. Yeah, you can see that like that. Yeah. So always emanate from the positive charge and terminate the negative charge. So that two charges placed and this system, we can say that dipole. Okay. Now, I will place this charge here and I will show the potential. Okay, sorry. For example, so here, for example, here electric field 1.81 volt per meter. Yeah. Okay. And also we can see that potential value, that is 4.0434 volt. Okay. 4.034 volt. Okay. So this is the potential due to positive charge. Note it down. Now I will place the negative charge here. Now you can see that value changes. Yeah. Yes. Now you can see that the value potential changes because of due to the negative charges present. Again, I will show that. So now note it down. For the fast charge, there is a potential, there is a electric field 1.60 volt per meter, potential 1.615 volt. We can choose any point in the space. So if we place the negative charge here, the potential is the sum of the, that is means total potential is the sum of these two potentials. So okay, okay, right. So this is sorry. Okay. So this is positive Q. This is minus Q. This is center. This is P. So if we place the potential, that potential means it's the total potential at the point P due to the sum of the potential due to the single point charge. And we have a formula for the total potential. That means, what is the formula? What is the formula of total potential at P? P dot cos theta by 4 by epsilon naught R square. Yes, correct. Okay. So this is a electric potential due to a dipole. Clear? Okay, good. Now we can move into that another one topic. Another one topic. Yes, sorry for that. In next class, Telugu teacher will come. Today, please adjust my class. Okay. Thank you. Thank you for understanding. Right. Now let's talk about special case, that is equipotential surface. So these are the surfaces where every point has a same potential. Underline that word, same potential, equipotential, equal potential, same electric potential. Okay. So equipotential surfaces mean in every point has the same electric potential. That means So you don't think about it like for every point potential, say there is a one potential, not that like that. In the same distance, all the point has the same potential. I will show the uh, animation. Okay. So the equipotential surfaces have two important property. One is they are always perpendicular to the electric field lines. Okay. So equipotential surface always perpendicular to the electric field lines. This is because electric field points in the direction of steepest decrease in potential, and there is no change in potential along the equipotential surface. Already you know that equipotential means, so plus here plus q minus q, so equal distance from the from both charges. Yeah, so this is the equipotential surfaces. Yeah, so equal distances. So because there is a electric field points in the direction of the steepest decrease in potential, there is no change in potential along the equipotential surfaces. So equipotential surfaces always perpendicular to the electric field lines. This is the first point, first key property. Second point, no work done. No work done. When charge, when charge, when charge moves along the equipotential surface. So, for example, this is a surface and this surface has a equal potential. Suppose if we move the charge from here to here, no work is done. Okay, because work done is equal to q dot del v. And del v means potential difference, because this point has a potential, this point has a potential, but here same potential. So 5 minus 5, 0. So 0 means 0. So there is no work done on a equipotential surface. So work done is also 0. Okay. So let's visualize this using a simulation. I will share the same animation now. Please wait. I will share the screen. Okay. So now I will choose this charge plus Q here. Okay. Right. Now I will place that potential tool here. Potential here. Okay. Now I will draw one circle here. Here you can see that the potential 5.938. So we can choose 5.9. Okay, like that. So that point is at some distance from that positive charge. Okay. Now again I will move the tool on the same surface. Here also you can see that 5.9. Here also you can see that 5.3, 5.938. Yeah. Suppose if we place the exact position, we can see that value of 5.9. So always equal to the 5.9. Okay, 5.9, 5.9. 5.9. Yeah. So now you can familiar with that potential. That means the potential at some equal distance from the charge equal. So this green line denotes the equipotential surface. Like that, you can move the same tool here. Okay. Now also I will draw the diagram, circle. So here 13.36. So potential high. Already I told you, very close to the charge, potential electric field high, and away from the charge, potential electric field decreases. Yeah. So now I will move the potential tool. You can see that 13.4. Yeah. 13.4, like that. Okay. So this is a equipotential surface. The equipotential surface always perpendicular to the electric field lines. You can see that, yeah, perpendicular to the electric field lines. And also, there is no work done when charge moving along the equipotential surface from one point to another point. Okay. Okay, good. Let's apply this concept by solving two numerical problems. First of all, problem number 1. An electric dipole with a moment p 4 into 10 power minus 10 coulomb meter is placed in a vacuum. Calculate calculate the potential at a point 2 meter away from the axial line. So away from the charge along the axial line. Okay, right, like that. So here the data are given. Electric dipole with moment. Already you know that. So if we have a electric dipole, we also have a electric dipole moment. So there, that is a value for this sum 4 into 10 power minus 10 coulomb meter, which is placed in a vacuum. We have to find the potential at 2 meter away from the charge along the axial line. Okay, right. So what is the formula to find the potential along the axial line away from the charge? We have a formula for the potential. Yes, that is V is equal to 1 by 4 pi epsilon naught P by R square. Yeah. Yes, correct. Yes, good. So here P, dipole moment 4 into 10 power minus 10 coulomb meter, or 2 meters, that is distance from the dipole center. This is the R. Yeah. And also we have a epsilon naught. Epsilon naught value 8.854 in 10 power minus 12. Okay, right. Already we know that 1 by 4 by epsilon naught value approximately 8.89, because 1 by 4 by epsilon naught 8.85 into 10 power minus 12. So we will get 8.99 into 10 power 9 Newton meter square coulomb square. This is a formula. This is a value for 1 by 4 by epsilon naught. So we can directly place that value in that equations. So 1 by 8.99 into 10 power 9 P 4 into 10 power minus 1, and R square 2 in 2 square. So okay, 2 square 4, because R 2 meter. Is there? Is it correct? Okay. 8.99 into 10 power 9. 4 cross 4, 1. So 1 into 10 power minus 10. So 8.99, 10 power 9, 10 power minus 10. So 10 power minus 1. Yeah. 10 power 9, 10 power minus 10. So we will get 10 power minus 1. So 8.9, 0.88, because 8.99 into 10 power minus 1 also we can write as here like that, 0.899 volt. So this is a potential at the point on the axial line is approximately 0.899 volt. Clear? Okay. So now we can move into the second sum. Please look at it. Okay, right. So we can move into the second problem. Problem number 2. Find the potential at a point 3 meter away on the equatorial plane. Equatorial plane of a dipole with moment P is equal to 610 power minus 10 coulomb meter. So here we have to find the potential at 3 meter away from the equatorial plane. Okay, equal distance of the dipole with the moment P is equal to 610 power minus 10 coulomb meter. For a point on the equatorial plane, angle is 90 degree because it is perpendicular. Is it correct? So we have to find the angle between center to that point. Like that. So plus Q minus Q. This is center. So this is 90 degree. Yeah. So 90 degree. So cos angle theta is 90 degree. Cos 0, that is cos 90 degree, which is gives 0. So potential is 0. Is it correct? Okay. Okay. So the potential due to electric dipole at a point on the equatorial plane is always 0 due to symmetry of this dipole, because angle is 0. Angle is 90 degree. So V is equal to 1 by 4 by epsilon naught P cos theta by R square. We can place 90 degree for the equatorial plane. So cos 90 is 0. So 0 into anything is 0. So V is equal to 0. Okay. So this results shows that potential depends upon angle. Potential depends upon angle. That is theta. You can see that. Suppose if you change the angle, potential also change. Okay. So very important point. The potential is independent of the dipole moment or the distance. It mainly depends upon the theta. Clear? The potential at the point on the equatorial plane is 0 volt. Clear? Okay. Right. Now it is your turn. I am sharing another Google form for a 5-question quiz based on today's lesson. So this will help us check our understanding. Okay. Okay. I will share the screen. Yes. Okay. Good. Right. First point, first question. If a point charge is moved, the point charge is moved from the point A to point B on the same equipotential surface, the work done is zero. Work done is what? If a point charge moved from point A to point B on the same equipotential surface, that then what done? Zero. Very good. Good. Zero. Okay. Good. Second question. The electric potential at a point on the equator plane of the electric dipole is the electric potential at a point on the equatorial plane. Zero. Yeah. Yeah. Now we did the sum. Yes. Zero. Very good. Zero. Yes. Correct. Then fine. Then third question: equipotential surfaces are already I told the two important property. What property? What property? Yes. Yes. Correct. So equipotential surfaces always dash B or A or C B. Okay. APS, APS. Yes, correct. Very good. Already I gave that notes regarding that equipotential surface. There are two key properties. One is work done is zero. Another one is equipotential surface is always perpendicular to the electric field lines. Very good. Very good. Great responses. Very good. So we can choose a option B. Fourth question, very important one. The electric potential due to short electric dipole at a distance r from its center is proportional to 1 by r, 1 by r square, 1 by r, r square or r. Electric potential due to short electric dipole. Already I told you. Yes. Okay. Okay. Good. Good. B. Yes. Yes. Very good. Great. Good. Yes. We can choose a 1 by r square. For a electric dipole, 1 by r square. For a single point charge, 1 by r. Yeah. So note it down. Clear. Very good. And the final one. The potential due to dipole depends on which which is the main term. I told that notes from the class. Yeah. Angle theta, charge magnitude, electric field strength, none of this. The potential due to dipole depends on, yes, 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 yes. Okay, very good. Okay, C, B, C, A. Okay. So suppose the formula already you know that 1 by 4 pi epsilon naught P cos theta by R square. Suppose we can choose that surface for an angle axial line or equatorial line. In both cases, only one term very, very important. That is angle. Yeah. So if the angle, yeah, yes, yeah. If the angle is 0 or 90 degree, it will impact the potential. Is it correct? So that's only in the problem number 2, equatorial plane. Theta is equal to 90 degree. So cos 90 is 0. So 0 is 0. So potential is 0. Clear? Okay. So yes, angles theta is very important uh, term, which is potential depends upon that term. Okay, right. We can check that answer. The point charge is moved from point A to on a same equipotential surface, or then always zero. Okay, good. The electric potential at a point on the equatorial plane on the electric dipole, equatorial plane, electric potential is zero. Okay, right. Equipotential surfaces are always perpendicular to the electric field lines. The electric potential due to short electric dipole at a distance from its center is proportional to the 1 by r square. The potential due to the dipole depends on angle theta. Clear? Good. Very good. So now I will share the screen for your homework problem. Okay, thank you. Yes, I will share the screen. Please note it down. Two important problem, two important question regarding your homework. First question, calculate the potential at a point 1 meter away from the dipole. P is equal to find 10 power minus 10 coulomb meter at a 30-degree from the action line. Second question, draw and describe the equipotential surface of a dipole and explain why no work is done moving a charge along them. Very simple answer. Work is zero, but because what? Because why? Note it down. Okay, clear? Thank you, thank you. Yes, thank you. Okay. So let's summarize. We have learned that electric potential due to dipole depends on not just the distance, not just a distance, but also angle related to the dipole axis. The potential decreases like that 1 by r square. Yeah, potential decreases with the distance as 1 by r square. And we also explored equipotential surfaces. So, which is the surfaces of constant potential or equal potential, constant potential, and are always perpendicular to the electric field lines. Always perpendicular to the electric field lines. Remember, no work is done. Move a charge along these surfaces. Okay. So this is a surface. So suppose if you move the charge from here to here, because already you know that the work is very much important, depends upon the initial and the final position. So for the equipotential surface, this surface has a same potential. So in this point, V is equal to, for example, 5 volt. In this point, also 5. So 5 minus 5, 0. So there is no work done because work is, already I told you, work is W is equal to Q dot del V. Q means charge, del V means potential difference. Okay, right. So that's why no work is done to move a charge along these surfaces. Clear? Right? So if you have any doubt, please ask me, or you can unmute yourself and um, you can say any concept, any uh, important notes from this class. Who would like to explain the concept of equipotential surfaces in your own words? Or you can describe the potential due to the dipole. One times question repeats, sir. Okay, I will share the screen. Yeah. Okay. Please note it down. Class is over. Jai Bharat, Jai Hind, Jai Vidyasati. Thank you, teachers. Thank you, my students. Thank you.